Good afternoon, everyone. A very warm welcome to Curious. My name is Martin Hendry. I'm Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow, and I'm the convener of the Royal Society of Edinburgh's Public Engagement Programme. So I'm delighted to be here to welcome you to our panel discussion, and I'm very glad that you've joined us too. Our theme today, from the cosmos to consumers, well, I think that will give us a theme which will prompt a very lively discussion. I'm looking forward to that. In just a moment, I'll welcome our panelists, and then I'll introduce our topic. We will all introduce our topic through a series of very short presentations, but there will be lots of time for questions and discussion after that. We're using the webinar format. There's people still joining, I think, as I speak. And that means that you can post questions via the Q&A box. So you should be able to see that in the bottom of your Zoom screen. And by all means, you can start doing that during the presentations if you wish. I'll keep a close eye on the questions as they come in, and then throughout the remainder of the session. I'll do my very best to bring everyone into the conversation, but given our limited time today, I hope you'll forgive us if we're not able to answer all questions, but we will do our best. So without further ado, let me invite our panelists to introduce themselves, and I think Giles is going to go first.
Thank you very much. Well, good afternoon, everybody. My name is Giles Hammond. I'm a professor of gravitational physics from the University of Glasgow. I've been working in sort of measurements of gravity since around 1998 when I did my PhD. I've also spent some time in the US working on the Advanced LIGO gravitational wave detector seismic isolation systems. I've been in Glasgow since 2007, and there I lead an activity to build the mirror suspensions for Advanced LIGO, and I also have a second research group which is looking at spin-off technologies, and we're developing micro electromechanical sensors as precision gravity devices. Thanks.
Thanks very much, Giles. And now we'll welcome Victoria.
Hi there. Sorry if I've got a bit of noise. My laptop's not happy right now, but I'm Victoria Martin. I'm a professor of collider physics as my official title at the University of Edinburgh. And I work research-wise primarily on two projects, both big collaborative experiments at CERN. So the first one is the ATLAS experiment at the Large Hadron Collider at CERN. And the second one is CLIC DP, and I'm not going to talk very much about that because we've actually got the spokesperson as one of the panelists as well. So, what do I do with these things? Well, personally, I'm very interested in the Higgs boson. So I'm sure people have heard about the Higgs boson. It was discovered 9 years ago now at CERN. But although we discover something, that's not enough. Of course, we always want to know more, and there's a lot more still to learn about the Higgs boson. So I'm using these colliders, ATLAS, which is running at the moment, and CLIC, which may or may not happen in the future, to learn more about the Higgs boson.
Thank you very much, Victoria. Next is Stuart.
Good afternoon, everyone. Pleasure to be here. So similar to Giles Hammond, I work in astrophysics. I should say I'm Stuart Reid. I'm head of biomedical engineering at Strathclyde. So I actually originally started my research career with people like Martin Hendry and Giles Hammond in gravitational wave detection, but been using some of these precision measurement technologies, and Giles was describing some aspects of that to transfer into other fields. And actually we're involved in stem cell research and applying vibration to stem cells to convert them into bone cells, which can then be used for surgical bone graft. And so at the moment, my research group, about half work on laser mirror coatings or gravitational wave observatories, the other half work on stem cell technologies. So yeah, that's my short introduction, and I'll describe a little bit more in a few moments.
Thank you, Stuart. So our final panelist is Aidan.
Yes, good afternoon, everyone. I'm Aidan Robson. I'm Professor of Particle Physics at the University of Glasgow. Like Victoria, I've worked for years searching for and now measuring the Higgs boson. More recently, I've been focusing in particular planning a next generation particle collider to come after the Large Hadron Collider. And so I'm leader of the Compact Linear Collider Detector and Physics collaboration at CERN, and also co-convener for physics for the International Linear Collider proposed for Japan. And I'll say a bit more about those things later on. Thanks.
Excellent. So a very warm welcome to everyone. We're going to do a very short series of presentations to set the theme of our topic today. And I'm going to go first. And I'm principally here just as chair, and we want to hear mainly from our panelists, but I wanted to just share a few thoughts with you about this topic. And going with the theme of from the cosmos to consumers, well, that's taking us all the way from the subatomic world to colliding black holes billions of light years away. But fields like particle physics and astronomy, and gravitational wave astronomy in particular, are unlocking the fundamental secrets of the universe through decades-long efforts by thousands of scientists across the globe, including, as you've just heard, leading researchers at several of our Scottish universities. So the breakthroughs that have come in these fields have been recognised in the conventional way by the academic distinctions, like, for example, 2 recent Nobel Prizes with strong Scottish connections. Firstly, in 2013 for the discovery of the Higgs boson, where the prize was awarded to Peter Higgs himself, as no doubt you will be aware. And then in 2017 for the discovery of gravitational waves, where the Nobel laureates were 3 senior members of the LIGO collaboration, but they explicitly acknowledged in their prize-winning lectures the contributions made by, for example, the scientists in Glasgow. But these fields are also driving innovation and technology, and that's what we're here to discuss today. They're shaping and improving every aspect of our lives, from medicine and security to environmental sensing and global communications. And the purpose of our discussion today is to share with you the stories of some of that technology. Now, cutting-edge innovation like that from the world of physics isn't new, because in the late 19th century, William Thomson, later Lord Kelvin, well, he was a pioneer of how to translate fundamental research on foundational concepts like energy and heat and electricity into commercially useful inventions. And in fact, his peerage was as much in recognition of his commercial and innovation success, what nowadays the research councils would refer to as impact, as it was recognizing his more fundamental work. So Kelvin's work on the electrical theory of telegraph wires, for example, allowed him to devise a method for successfully sending telegraph signals along undersea cables. And in 1858, Kelvin was on board the steamship Great Eastern when it laid the first transatlantic telegraph cable. That was a quantum leap for global communication, every bit as important as the creation of the internet in the more recent past. And Kelvin's breakthroughs in our understanding of thermodynamics, well, those would ultimately underpin the technology of things as everyday as refrigeration. You see that in this advert for fridges from the 1920s, where they were referred to as Kelvinators. So who are the modern day Kelvins, and what are the technological breakthroughs that physics is bringing to 21st century, to medicine, to communications, and to commerce? So over now to our panelists. And again, we're going to hear from them individually first before we open out the discussion to all of you to ask questions about this fascinating topic. So we're going to begin with Giles.
Thank you very much, Martin. Of course, it's a real pleasure to be talking about my work here in gravitational waves. So, as I said, I'm from the Institute for Gravitational Research at University of Glasgow. So this slide here shows some of the work that we do in what I'd call the fundamental physics aspect of the research group, and that is building the most sensitive length measuring devices in the world, which allow us to probe the most extreme astrophysical events. So we're looking at colliding black holes, colliding neutron stars, but we're looking at that with terrestrial observatories at the moment. So what you can see here on the left-hand side of my screen is one of the mirror suspensions that we build, and this is where with Glasgow we lead the activities, and we build these suspensions for Advanced LIGO, which is a US-based detector, and we hang these mirrors at the bottom, these 40-kilogram chunks of fused silica. We hang them with fused silica fibers. So we pioneering that technology. That was essential in order to lower the noise level of the detectors to allow us to see these tiny ripples in space-time, which are due to these cosmic events. Of course, we don't stop there. We're developing a new field. So we're looking at building these detectors, improving the detectors, really turning the field into an astronomical observation tool. So just like you use electromagnetic telescopes, we're now sort of laying the foundation, and with our first sort of 50, 60 detections, we're starting to develop the field of gravitational wave astronomy. So using gravity to actually probe the universe. And of course, coming online in the next few years, we're always sort of innovating and developing technology. So we're looking at the top left, right there, you can see this is a detector that's going to go into LIGO. It's going to be a LIGO India detector. So I lead a UK effort to put a third LIGO detector into Maharashtra. And that's in collaboration with our Indian colleagues. And then on the European stage, we're working on putting detectors underground. And that's what we call the Einstein telescope. And this is a triangular detector of 10-kilometer arm lengths. And that will allow us to sort of probe the entire universe of binary black hole systems, for example. But of course, pushing these fundamental technological limits allows you to develop new spin-off technologies. So this is, I've got a couple of slides just to show you some examples. So when we build our mirror suspensions, we have to bond and joint together glassy materials, so fused silica, for example. And this has applications in development of telescope mirrors. So you can see here in the top left, this is a low expansion glass top plate and bottom plate bonded to a heavily lightweighted telescope structure. So we can bond piezos to those mirrors to allow us to flex the mirror to take account of aberrations in the upper atmosphere. And that's working with a company down south called Gooch and Housego. We developed sort of extremely sort of stable and robust optical setups, which can be launched on satellites. So this is in collaboration with Astrium, and this is a detector that's gravitational wave detector that will go into space, probably 2035. And then we're also bonding together sapphire, and that's got applications in areas where you need high thermal conductivity, so laser applications. Of course, we do a lot of sort of hunting for signals in noise, and on the right there, some of our collaborators on the data analysis side, they use some of the algorithms that we and the statistical techniques that we use in gravitational wave astronomy to improve retinal scanners. So working with a company called Optos, which is over on the east of Scotland, to sort of stitch together and understand some of the artifacts in these images. So for example, if you blink your eye, you can use machine learning techniques to throw away the bad frames and keep the good ones, and that allows you to improve your efficiency of the sensors. And then finally, an activity that I'm leading, my second research group in Glasgow, is we're building precision microelectromechanical sensors, and that's in collaboration with a company called Kelvin Nanotechnology in Glasgow. And this is the little cell here. It's just to give you a scale, across here is about 10 millimeters. So these are sensors that can be used in a number of areas. So environmental monitoring, defense and security. And we've just got, as we speak, one of my PhD students, you can see him sitting here. This is over on Mount Etna at the moment, and he's just installing our first MEMS sensors onto the side of Mount Etna. And we're going to use these sensors to be probing inside the volcano using gravity to understand the magma plumbing in the Mount Etna system, and use that potentially as an early warning system for predicting eruptions.
Thank you, Giles. So I think Victoria's going to take up the baton next. Over to you now, Victoria.
So what I have here, let me just move this one out of the way, is a picture of the Large Hadron Collider. So obviously this is not really the Large Hadron Collider. This is a picture taken from an aeroplane looking down over Geneva. And what you can see there, that's Lac Léman, Lake Geneva. And then imprinted in this yellow line here is where the LHC, the Large Hadron Collider, is. So the Large Hadron Collider is an atom smasher. And what we do is we take protons. So protons are the center of hydrogen atoms, and we speed them up almost to the speed of light. We can't get faster than the speed of light, but almost the speed of light. And we have one set of protons going around the loop one way, and another set going around the loop the other way. And then at 4 points during the ring, instead of them kind of going past each other, we steer them so they hit head on. And essentially the ATLAS experiment and the other experiments at the LHC, they just observe what happens when we hit these two protons together at incredibly high energies. And I mean, it sounds simple to say, but it has taken years of building and construction and understanding what's going on. So I'd like to, so to do that, we've had to develop a lot of technology. So this other picture that I'm sharing now is, well, it's a kind of portmanteau picture of what actually happens in the LHC. So the LHC is 100 meters underground. So this is a tunnel 100 meters underground. And what you can see is what we call the beam pipe. And that's where the beam of protons, so we don't just get one proton at a time, we have them in a beam one after each other, where they are accelerated to the speed of light. And then it's cut away. It's not cut away in real life, but in this picture it's cut away so you can have an idea of what's going in there. And then these little lines here are supposed to represent the two proton beams, one going clockwise and one going anti-clockwise. So how do you even do that? So there's in the area where the protons go, we have to have an excellent vacuum. And to make a vacuum, it's fairly simple. In principle, you just soak out all the air. And so you have a vacuum. And the reason you need a vacuum is those protons going along, they could bump into the air molecules, and that would really kind of upset our situation. So we take out as much air as we can. In fact, we have the best vacuum, the best large-scale vacuum that we know about, because it's a 27-kilometer circular vacuum. So we've had to develop a really excellent vacuum technology for that. The other thing is those protons are really energetic. They're going almost at the speed of light. And momentum tells us that if you're going very fast in one direction, you really want to stay in that direction. Now that's not very good if you want a collider, at least a collider like the LHC. We don't want the protons to keep going straight. We actually want to turn them around. So they go round and round the loop, which you can maybe just see in my background now. So we have to stop them going straight. And for that we use magnets. So we use magnets to just deflect them very, very slightly to go all the way around the 27-kilometer loop. So they can come back and we can accelerate them a little bit more, and then eventually we can collide them. So these are two of the really driving technologies that we've developed at CERN. They are used not just at CERN. We do share them with other labs. I'd say they were definitely one of the leaders in this vacuum technology and this magnet technology. But they do have more practical spin-offs. So, for example, solar panels need a vacuum in it to act efficiently. And the same technology that was developed for the LHC to take the air out and create a really good vacuum has been applied to solar panels. And those solar panels now are installed on the roof of Geneva Airport. So that the energy, the electricity that runs Geneva Airport uses CERN technology. And that's one example of something that was developed for CERN, for high energy physics, that now is in everyday use. Another one that I'll just mention, and maybe we'll come back to talk about a bit more in the discussion session, is computing and data. So in the LHC, the protons collide 40 million times a second. And our detector is essentially like a digital camera, 100 megapixel digital camera. So we're taking 100 megapixel digital images 40 million times a second. And that's just Atlas, my experiment. There are another 3 experiments as well. So that creates a huge amount of data. And so CERN has had to develop its own data management policies, and also data sharing policies to send the information out, not just at CERN. It's not just people at CERN that want to see it. It is people like me in Edinburgh and Aidan in Glasgow and our colleagues in Paris and Berlin and Istanbul and New York and Johannesburg. So we have very good distributed computing. And a lot of this has formed some of the basis for the current cloud computing models that are out on the market as well. So that's just a couple of examples of what we do at the LHC and how it has come out slowly to consumers.
Thanks very much, Victoria. So we'll pass on now to Stuart.
Yeah, really pleased to have the opportunity to come along and chat, and also always good to go after Giles Hammond, and he's set some of the scene for us. But my original field of research is in gravitational wave astronomy. So as Giles described, as shown in the top middle picture there, we build these very large observatories. They're not observatories for light, the electromagnetic spectrum, but for detecting the gravitational signals from astrophysical events, such as black holes colliding. And inside this facility, we have these 4-kilometer arms. We send lasers down. We reflect the lasers off mirrors, and you see a picture there. Giles had also shown a mirror. These are 40-kilogram mirrors, reflect the light back. And we use the lasers to measure the position of these mirrors. And so the challenge that Giles Hammond, myself, many others, across the UK and US and other countries, spend a lot of time trying to make these mirrors the quietest place on Earth. But the technology that I'm involved in is actually making these mirrors very reflective for the laser light. So not only the quietest place, but also the shiniest place on Earth. And so we use a coating technology, and the analogy might be if you see oil and water and you see the thin layer of oil and then you see the rainbow kind of colors, that's because when the oil becomes very thin, it interferes with the light, and then depending on the thickness of the oil, it reflects different colors, and you see the rainbow pattern. And we basically make these mirrors reflective by placing many thin layers of materials, which are very carefully tuned so that they reflect one color of light, and that's the color that the laser operates at. And that's because we need the laser to hit off these mirrors, all the light to be reflected, because we use that light as the signal. Giles had mentioned trying to suppress the noise, but as part of that we also want to increase the signal, so we want to use all of that light to measure the position of these mirrors. And so although these are very thin coatings, directly above my head there you can see one of the systems in construction just near Glasgow Airport, which will be able to coat 60 centimeter diameter mirrors, 200 kilograms each. And so these are some of the mirrors required for future observatories like the Einstein telescope that Giles had mentioned. So there's lots of technology, again, as we were hearing about today, going into these large scale experiments. When we think about applications, other applications of this technology, of course, laser mirror coatings, you might imagine other laser applications. And the biggest industrial driver, commercialization driver for optical coatings just now for laser applications is the laser damage performance. So that's how much laser power you can either reflect or transmit through your optical coating before the optical coating breaks down because of heat deposited or some other effect. Now you might think, okay, these are just large power laser applications, but actually that's not the driver. Consumer products drive the miniaturization of laser devices. And even if you think of the VCSELs on your phone, which project laser spots on your face for the facial recognition, I mean, you don't see that because it operates in the infrared, but this technology, people want to be miniaturized because they don't want massive phones with big optical systems imaging your face. And we also, work with a Scottish company called Helia Photonics in Livingston. They make very, very small laser diodes which go into the Audi A8 for pedestrian sensors. And so the big consumer drive, the drive for consumer products using laser technology is laser damage performance. And so actually the University of Strathclyde, Glasgow and west of Scotland, we're creating this, what we call a test bed. It's just a centre really near Glasgow Airport as part of the National Manufacturing Institute Scotland, which is a Scottish Government initiative where we're actually taking the coating technology that we have developed for the astrophysics projects, placing it within this centre and allowing photonics companies and local industry across Scotland and the UK to come and to see whether this technology might be useful within their production lines. And so laser products is one. The one which might seem a little bit more strange as an application coming out from the astrophysics work, but as we've been describing, gravitational wave detectors require very sensitive displacement measurement of our mirrors to see how these mirrors move due to the disturbance in gravity caused by astrophysical events. And so we use some of this precision measurement technology to look at trying to apply vibration to stem cells. And back in 2013, so way over on the other side of the slide to me, The BBC covered our discovery where we found that you could shake stem cells taken from adult patients. These are mesenchymal stem cells that form connective tissue in our bodies, so bone, tendon, cartilage, muscle, and probably not what patients are crying out for, also can form fat. And we found that if you shake them 30 nanometer amplitudes, so if you scale the cell up to the size of a football, it's about the same as sliding in one sheet of paper underneath the cell and out again. But 1,000 times a second, it really strongly persuades these stem cells to turn into bone cells. And so it's drug-free, scalable, technically it's cheap, and therefore it's safe and practical to use as a way of generating surgical bone graft tissue that can be reintroduced for patients. And the Sir Bobby Charlton Foundation, so the famous ex-Manchester United football player, has been using his funding within his charity to help translate this for people who have been injured by landmines, so civilian landmine injuries, and trying to change the outcome for these patients by basically implanting enough bone to maintain enough bone within their legs so that they're not confined to a wheelchair but can have a prosthetic fitted or something. And that will have clinical trials in Glasgow next year. Another application is, rather than taking stem cells out from the body and reintroducing them to the patient, we've also been looking at trying to create wearable devices that basically apply this vibration. I mean, similar to wearing headphones, but this has been with the spinal unit in the Queen Elizabeth University Hospital. And so trying to see whether we can use this type of nanoscale vibration to promote bone health or bone healing. And so we've been looking at osteoporosis, which is something which many people suffer from, but in the case of people who've had severe spinal cord injury, the rate at which bone loss occurs is very rapid. And so we've been looking at trying to use this to slow that down or potentially reverse and improve bone health. And so we've been looking at not just the laser applications, but also some of these healthcare applications as well. And I will stop there.
Thank you, Stuart. So over now to Aidan to round off our journey through lots of examples from these two fields.
Yeah, thanks, Martin. So I've brought along two examples relating to my research where technologies that we've been developing have found really interesting other applications. One of them in accelerator technology and one in detector technology. So as I said at the start, my main research interest just now is in building a very high energy collider to come after the Large Hadron Collider. It'll be a Higgs factory to produce millions of Higgs bosons. And the fundamental physics motivation for that is that the Higgs particle is entirely new. It's not like the matter particles and the force particles that we've known before. It interacts completely differently. And so understanding those interactions gives us a really new window into fundamental physics. And one way of building a Higgs factory is to collide electrons and positrons at very high energies, and that's what I'm interested in doing. So to get to very high energies, you need a very high accelerating gradient. And a lot of work is being done in our collaboration, the CLIC collaboration at CERN, to increase these gradients. So in other words, to get a higher energy and a smaller length of accelerator, and also to do it at room temperature rather than at very low temperatures. And we're now achieving gradients of millions of volts per meter. Now, for a collider, you need tens of kilometers of this thing, but these recent advances mean that you can reach electron energies that are interesting for radiation therapy, for cancer treatment in just a few meters. And this is one of these structures, I hope you can see behind me, one of these accelerating structures which supports really high frequency radio frequency power and can let us get to very high accelerating voltages for electrons. So a few meters of accelerator is something that you can build in a hospital. You can mount it on a gantry, you can swing it around a patient, especially when this is all operating at room temperature, in a way that's just not possible for longer accelerators. So this accelerating technology breakthrough has enabled a whole new class of treatments, or is enabling a whole new class of treatments, reaching tumors that are quite deep, but that could not be reached by electrons before, because lower energy electrons are just less penetrating. And so teams are using our test facility at CERN to understand the behavior of the beam in material that resembles our bodies, and also to investigate the use of high, very short doses, which seem to be more effective. This is called flash therapy, and in this case with electrons. So a prototype facility has been announced with the Lausanne University Hospital, and the aim is to deliver highly targeted beams capable of reaching deep inside a patient's body, but with much fewer side effects. So this is a direct consequence of advances in linear acceleration technology achieved by the CLIC collaboration at CERN. We're trying to build a Higgs factory, but I think a particularly interesting aspect of this example is the timeline, because the use of these accelerating structures in a collider is at least a decade away, but they'll be used much sooner than that in hospitals. So then the second example on my other slide here is from the detectors that we use to measure particles originating from collisions, for example, at the Large Hadron Collider, and in particular silicon detectors, which are a speciality of both Glasgow and Edinburgh universities. And what you see here is a chip from the Medipix family of electronic chips. They were originally developed for the Large Hadron Collider to read out our detectors. And it works a bit like a camera. So it detects and counts individual particles hitting the pixels when an electronic shutter is open. And so this allows really high resolution, high contrast, very reliable images. And it was realized that that's also very useful for imaging applications in medicine. So this has been going on for a while. Glasgow was one of the founding members of the collaboration. But as the technology has got more and more advanced, the chips can now separately record different energies of X-ray photons hitting the detectors. And that means that it can identify different components of body parts, like fat, water, calcium, and markers for diseases. And so if you think of a traditional X-ray image, it's kind of shades of gray, but this technology extracts much more information from the X-rays that are going through your body, leading essentially to a kind of color X-ray image, where, for example, blood vessels can be seen really clearly in addition to the bone. And so this is really exciting. And there are many other diverse applications of this Medipix family of chips. These devices were recently used to prove the authenticity of a painting by Raphael through detailed analysis of the composition of the paints. They're installed in the International Space Station as radiation monitors, and schools in the UK can borrow them as part of the Research in Schools programme to do some experiments on cosmic rays and on nuclear and particle physics. And actually, one of my students has just completed her PhD characterising a new prototype Medipix family detector for use in our future collider CLIC. Since I'm the final speaker, maybe just to sum up, I think that both particle physics and gravitational wave astronomy really necessarily sit at the interface between fundamental science and technological breakthroughs. And so I hope that these examples just give a sense of some of the ongoing, maybe slightly surprising tangential outcomes of our work. Thanks.
Thank you very much, Aidan, and thanks to everyone for giving us that great overview. So it's now in the second part of our session. Really over to our audience to pitch in with some questions and comments of their own. I have one from Jack Martin that's very interesting. It's sort of picking up perhaps on some of the things that Victoria was mentioning about the computing and cloud computing and the vast number of collisions and all of that huge amount of data that the LHC generates. So Jack is asking, as with Galaxy Zoo, can citizen scientists analyze the data? So there's a way to answer that in the context of gravitational waves, which I'm happy to pick up, or Stuart or Giles might want to, but I honestly don't know myself what citizen science opportunities there are in particle physics. So I wonder if Victoria has any thoughts on that.
That's a kind of on the spot question, Martin. Yes, we do have some citizen science projects where you can come along and look at the data, but at the top of my head I cannot remember the name of them, so maybe I'll try and find that out during the session, and I can put the link in the chat or let people know. But yes, there are opportunities.
Absolutely not a problem. And it's interesting to contrast the desire to involve citizen scientists in our research now, perhaps with how things were done back in Lord Kelvin's time, when it was somewhat more esoteric and in the domain of a small number of individuals to carry out research. But it's really good that so much of it is now shared. So again, this falls a little bit more in the data analysis side of gravitational waves, but let me just see whether Stuart or Giles would like to comment on this first, or if not, then I'll be happy to talk about Gravity Spy, as you will know, is the relevant theme here.
Yeah. I mean, I don't mind, happy to say something. I would have said exactly the same thing, Martin. I would have. So yeah, absolutely. We do have sort of citizen science projects ongoing. And part of we have a lot of public outreach within the gravitational wave community. And one of the things that's come out is the real need to characterize these detectors. We've shown you some beautiful pictures of how the detectors work, but when you really dig into them, there's always sort of little sort of bumps and glitches and niggles that we're always trying to understand. And this is a perfect type of application where we're trying to classify all of these different effects that can cause our mirrors to fluctuate at 1,000th the diameter of the photon, which is where our gravitational wave signatures come from. So what we like to do is we're trying now to utilize sort of machine learning techniques to sort of look at these effects and start to understand, you know, is it due to a bird pecking on the vacuum pipe, which we've seen before, let's say, or is it due to a helicopter, or is it due to one of our RF amplifiers that's sort of blown one of the resistors? All of these structures that we see in the gravitational wave signature can all be a little bit different. So we have to sort of classify and understand the, if you like, the training set of data with which we're going to sort of then apply our sort of machine learning algorithms. So there is a project ongoing, and it's through Zooniverse. So you're a great question to pose. But Zooniverse is one of these ones where you might be classifying galaxies. But we have one called Gravity Spy. So if you do search for Gravity Spy and Zooniverse, then that should take you to a link where you can start going through some gravitational wave data and start sort of identifying these different sort of glitches that we might see in the detector. And then that directly helps us in sort of then characterizing how the detectors perform, ultimately to try and improve the signal to noise of these instruments.
Thanks very much, Giles. So Victoria's having a look for some further details on the particle physics side. For
Martin, I did already find one. I just
Splendid.
So I put it in the chat answer, but if you search for Atlas at Home or LHC at Home, you will find where you can help with our generating some of the simulated data. We need to understand the actual data that we take as well.
That's terrific. Thank you, Victoria. And another aspect of this, I think, is the potential use of real data from the detectors in the educational context. So not necessarily to make new discoveries that haven't been made before, but to allow high school students to experience what it's like to analyze real data. And I know that's something Aidan's been deeply involved in. Would you like to talk briefly about that, Aidan?
Yeah, thanks, Martin. That's right. So again, this is in the context of the Atlas experiment and your previous similar collider experiments, where we've tried to capture this idea of discovering a process and something that can be done in a classroom on the time scale of about half an hour or 45 minutes. And so I agree, it's not quite the same as really harnessing the brain power of the general public to look for anomalies in the data. It's more like repeating things that we've done before. But I think it's exciting for school pupils to know that they're looking at real data and making selections and seeing a peak appear over a falling background. And so we try to encourage people to shout discovery when they get their significant signal. So there are a few examples of that.
Thanks, Aidan. So we have a question from Alison, and I'll maybe direct this one to Stuart, because I think what Alison is highlighting is the need to ensure that more people understand and value the real and direct benefits of fundamental physics to their day-to-day lives. And I think some of the examples that you cited, Stuart, are very good exemplars of that, where, as you said yourself, the applications can be in quite different fields. So how do you think we can do that better?
It's difficult to give a holistic answer to all, but I mean, it all comes down to communication at some level, because it's how we communicate that. And obviously there's some mention of working with schools, and Aidan and others are very much involved in that, and that's clearly one key area, is to make sure that at the early levels that people going through the school system and learning about physics and all the processes realize that there's still a lot of worth in doing fundamental research, because it almost always generates impact down the line, because technologies are progressed, and we see that as examples in our field. And I guess one of the things that we need to explain to people is that you can't always predict what those are. I mean, I don't think really many of the technologies and the spin-offs of those technologies that we've all been describing could have been predicted 20 years ago. very easily, but yet they've happened, and I think that's always the case, and I think that has to be communicated. And I guess the other thing is to try and communicate with the wider public. So I mean, schools is obviously one key area, but we've all been involved in big science exhibitions. I mean, there's one, the biggest public science exhibition is held each year in the Royal Society in London, and I know that all of us have been involved in that. And obviously there's activities that often happen in Dynamic Earth in Edinburgh, at the Glasgow Science Centre, and so I think there's activity in those areas, but I think it's a challenge for all of us who still work in fundamental science to find better ways to explain its benefits to people, and also to make it understood by the taxpayer how much we appreciate, the opportunity to progress these research areas, because it's a real privilege for us, and I think it's not always communicated back, exactly, how fortunate we are to be able to be working in these fields and to see the impact. And obviously it's our desire that others would see that impact and understand the benefits that come from it.
Thank you, Stuart. So we have a question now from Carolyn, and I think it's appropriate to put that to everyone, really. Carolyn's asking, what applications do the presenters feel most excited about in terms of not just consumers, but of wider society in Scotland? So Giles, do you want to go first? Well, what excites you most about all of these applications?
Yeah, so, well, I mean, I will sit slightly on the fence here, because I would say that, all of the applications in technology that we've heard about today are just really exciting. I really like, when Aidan, I don't always sort of know what's going on, at the detailed level from different areas of physics. But actually, one thing that really excited me was this development of the technology for these sort of smaller, better accelerators. I'm currently sort of trawling through a number of grant proposals where we're looking about sort of commercialization of technology through one of the funding councils in the UK, and this is a medical kind of call, and just to sort of drive for making things like proton beam therapy more available, to allow better sort of treatment, more throughput of patients. I see this is these can be real game changers. There's very few centres in the UK and worldwide where we can do this kind of treatment, and they are really remarkable things, these therapy centres, because they're sort of maybe 100 or so ton gantries that have to move around a patient. If you can do this and change this and make it into sort of meter scale accelerator technology, that has a huge sort of benefit and sort of game changing application. So in a way, for me, it depends on the stakeholder who I'm working with. So if I was thinking about sort of, let's say, sort of 40 to 60-year-olds, I think accelerator technology and cancer therapy, cancer treatment is really a sort of exciting area. It's going to sound awful that I of course, my own technology, I think the really exciting thing for me is actually making that transition of getting devices from the lab out into the field. And that should never be underestimated, because I work on Etna, for example, which I find really exciting, taking gravitational wave science, but applying it to things like volcano monitoring, but also water table monitoring. So we are working with a number of partners in Africa to actually do gravity surveys, to look at how to manage resources and water. We're working with civil infrastructure in Brazil, learning how to use gravity sensors to understand what are called these tailing dams. And of course, we've seen in the media before these awful sort of catastrophes where one of these dams has failed and has flooded a village. So you can actually use the technology to actually understand when things are going to fail. So I think that's quite exciting. From a Scottish perspective, with COP26, gravity sensors can also be utilised to understand how do you better understand carbon capture and storage. So I think that's naturally one that sort of applies to a really broad sort of stakeholder engagement, both from school children all the way to society. So maybe I haven't really answered your question, but I think it depends on who you really talk to.
Yeah, no, it's a good point, Giles, and I guess for everyone, they personally will be excited by different things, but as you say, it will be the stakeholders that will be excited by different things as well. Indeed, Carolyn had also referred to how we excite the next generation of scientists who are currently going through our school system, how they can see that technology shaping the world of the future. So as you say, things like COP26 provide a great lens for that in terms of what are seen as the global challenges that those generations will face. Anyway, you don't want to hear from me, but want to hear from the others. I wonder if I might maybe just keep that idea of what excites us about innovation in mind, and we'll weave it into some other questions, given that we have limited time. I mean, one question that you picked up on, Giles, that I would like to ask Aidan a bit more about is about the Lausanne hospital trials. So that struck me as a little different. I think you alluded to this yourself, Aidan, from the traditional approach where the innovation happens and then perhaps years or even decades later it's commercialized. So does that create any tensions in terms of your scientists trying to crack on with getting click going, while simultaneously you might say being distracted by the applications in Lausanne?
No, I mean, I think it works amazingly well synergistically, and because we're talking about a really fundamental acceleration technology, there are actually other applications of that as well to make free electron lasers, which would be a much smaller scale than the collider that we want to build, but would be kind of intermediate between the hospital-sized thing and what we would ultimately like to do for particle physics. So I think having that wide interest just helps helps move the field forward. We need to work out how to manufacture increasingly long components. Essentially, it's the to support the sort of gradients of 100 megavolts per meter. You need extraordinarily flat, smooth surfaces. And you need industry to do that for you. You need industry to be interested in doing that. And so the more applications that you can find for it, really the better. So I agree, Martin, actually, in this particular example, I think the very close involvement of the hospital comes at a particularly early stage. But in a way, I think referring back to the previous question, what we're most excited about, I think it's really hard to know what is going to have a big effect on other people and wider society. And that's certainly true of fundamental physics, but I would say even now at the sort of stage that we've all been talking about, where you're just beginning to transfer something out from fundamental research into applications, we still don't really know, what will come of those things 5 or 10 years down the line. But yeah, I think trying to get people involved as early as possible is really helpful.
Thanks, Aidan. I'm going to quickly go back to Giles. He's promised to be brief, but there's a question, a follow-up to one of the things that Giles talked about. And Giles, over to you.
Yeah, thanks. No, I see the question from Susan, and I tried to type an answer in, but I think I clicked the wrong button, so it said answer live. Regarding blue carbon, absolutely. So this is about putting, I guess, CO2 into marine ecosystems. So there is a big push to put sort of gravity sensors onto submersible vehicles, where you can actually sort of go under the water and actually monitor where you're sort of pumping the carbon. And what you need to do that is make smaller, lighter, cheaper gravity sensors. And that's really where we're trying to push the technology, because currently a gravity sensor costs upwards of £100,000, and we're trying to reduce that cost by about a factor of 10, which means you can have arrays of gravity sensors, make them small, put them onto submersible vehicles, and then actually do the monitoring, so you understand where you're putting the carbon into the ecosystem. So yeah, absolutely.
Thank you very much, Giles. Okay, so I'm going to turn now to Victoria. So Victoria, what excites you about some of the innovations that you just shared with us?
So what I find really exciting is actually CERN's approach to knowledge sharing. So CERN develops a lot of its own software and indeed a lot of its own hardware. And a lot of that, or most of it in fact, is shared. So you can, for example, if you felt like, you could download and use the code that we use to analyze all of the Atlas data. That is public and available for everyone. But that's probably not very useful to most people. But something else CERN has had to do, as an example, is manage all the papers that we produce and all the documents we produce, the photos and the reports and indeed the data. And the software that we have to manage that, kind of library management software, if you like, has been released to the public, and you can go to the CERN webpage and you can download it and you can use it. It's not just software that CERN has been sharing, hardware. They have an open hardware license whereby some things that they design, you can find the blueprints again on the CERN webpage and you can download them and you can make them yourself. So it's had a very open policy towards sharing things. I mean, actually the best example of this, the one that's probably familiar to everyone, is the World Wide Web. I mean, that was developed at CERN not so we could read the news or we could book holidays. It's so initially, so CERN scientists who were, again, in different countries could have a look at the same information at the same time to see what was happening with their experiments. And now it was released to the public, and now, you know, we all use it every day. So I think that's the most exciting thing for me, just the very openness of the approach that CERN has. And the reason it's like that is because it is a lab that is funded by many countries. So it is not a French lab, it's not a Swiss lab. As I like to tell people, it's Scotland's laboratory for particle physics, as well as the French laboratory for particle physics and the Dutch laboratory for particle physics. It's for everyone. And that's why we share the things with people that want them.
Thank you, Victoria. And that, I think, is a theme that one sees in the gravitational wave astrophysics side too, very firmly. The great strength that comes from the whole world basically working together on these sorts of projects. Stuart, over to you now. What would you think of as exciting, most exciting from the various projects that you shared with us?
Yeah, I mean, I think the thing which excites me the most, ignoring my own particular research, because it is, as has been described, it's always exciting to see work that you've been involved in actually reaching, you know, some kind of impact and benefit for others in society. But even just hearing about, you know, Victoria's mention of the technology which is helping with, you know, the solar panels and photovoltaics. I mean, clearly, when it comes to impact from fundamental science, the main area that we need that in the coming years is related to the climate, and obviously some of the questions and comments have been related to that. I mean, this is always kind of a tricky balance which we face. I think that the funders, you know, associated with the government and also the researchers is, you know, how much do you allow fundamental research just to freely go about doing its thing, and how much do you try to say you have to justify yourself by also generating impact? But, you know, it excites me to see that there are areas of technology that could be used for helping to address the climate issue. But although that's also very exciting, it's challenging that, you know, there's a lot to be done in relation to the climate, and, you know, it would be good to see further, you know, technologies that could generate clean energy, technologies that can help transform our food industry so that the burden from that on the environment is significantly decreased. And so yeah, it's exciting seeing the technologies, but also a little bit challenging just to see like what needs to be addressed in the coming years, really, for the benefit of society. And I guess, you know, from my own research and the bone health related stuff, you know, it's really good when, you know, we have an aging society and more people are living to an older age. You know, it's nice to also see technologies that can help assist and improve people's quality of life, you know, later, particularly later in life. So that excites me too.
Thank you, Stuart. And I think that's frankly a good point to move towards our conclusion. Again, what I'm hearing from all of you, it echoes very much with my own thoughts on this, that I think the way in which we do big physics as an international collaborative endeavor, you know, gives me confidence that if we can tackle these big fundamental physics problems by working together across the world, you know, it gives me confidence not just that we've got the skills to tackle other societal challenges, but that we've also got the right mindset and approach to do it, that we will achieve more by working together. And again, you know, it's good to reflect on how, at least in the last year and a half, there's been a great deal of global cooperation to do with the vaccine programs, for example. And indeed, even fundamental physics had its role to play within that, using some of that cloud computing we heard about from Victoria to do many of the calculations involved. We hope that we've given you a sense of the rich variety of applications that there are in fundamental physics and how those are affecting so many different aspects of our world. And well, we wish you all a pleasant afternoon, and thanks again for joining us today. Bye-bye.